This is the worked answers to page 7, right? So I will post just the sheet filled in for you as well when I've got this. So, but it's just for anybody who needs talk through it. Okay, so let's see. Okay, so first one is F2. Okay, so that should be straightforward enough. Now you've got 7 electrons. If we just do, right, there's each fluorine. Okay, and they will come together to form the F2 molecule. So when you're putting them together, just make sure that it's obvious that they're shared electrons. Don't have them like miles apart, okay? Because if they're too far apart, it looks like ions, okay? So this would be wrong. Or could potentially be misinterpreted, because if you think about it, that's like a fluoronium ion, and that's like a fluoride ion, okay, and it's not that. Okay, and what was the other thing I asked for? Thick diagram as well, so it's just that. Okay, straightforward enough. Will I skip the easy ones? I've already done ammonia. Oxygen, I'll just include those. I won't work through those ones. I'll start on number 7, okay, PF3, because that's actually okay, so PF3, right, so how does this work? Now, if we do the phosphorus atom, and we do the fluorines, okay, so what happens here is this 3 unpaired electrons, right, and you've got 3 fluorines in total, so you're going to form the covalent bonds around here. So you're ending up with P with a lone pair, dot X, and then covalent bonds with fluorine, and then just put in all the other fluorine electrons. Don't forget to do that when you do these kind of diagrams. Okay, so that has 1 lone pair and 3 bonding pairs, right? And it's P. It actually would have, oh, let's just do it like that for now. Although in reality, you'll find out it's actually trigonal planar, sorry, trigonal pyramidal, and it is, right, that's not the way it actually have that shape. Okay, anyway, then we'll come to that. Right, next one, 8 is PF5. This time I think I'm going to change the color of the electrons for one of them. Make fluorine the dots because X will take longer to draw. And phosphorus here is XX. Now, you might think, okay, it's got 3 unpaired electrons, true. This time, it's going to form 5 single covalent bonds to the fluorines. Fluorine is very bossy, if you like, as a bonder. It will force atoms to have more than 8 electrons in its outer shell in the end. So let's put them like this, P, F, 3, 4, 5, okay, and let's put, so we've got X, and then the dots, so shared pairs, only shared pairs of electrons, and phosphorus now has no lone pairs left. The fluorines they do have 8 electrons in their outer shell. That's generally the case for the outer atoms in a molecule. They'll tend to obey what's called the octet rule, having 8 electrons in their outer shell, and the central atom will be the one that doesn't. Okay, so actually we're going to meet the octet rule next. If you look back at this, See that this is straightforward enough. There's 8 electrons around the outer shell of phosphorus and fluorines. All of those have obeyed what's called the octet rule, right? But if you have PS5, it doesn't. Okay, phosphorus is 2, 4, 6, 8, 10 electrons around its outer shell, right? So but remember, I mentioned earlier that the rule is that all electrons are paired, and you can, and maybe phosphorus is a bit bigger, it can handle more than 8 electrons in its outer shell. Okay, and how do you draw this? This is so P, so you could just do 1, 2, 3, 4, 5. And just to mention it, in reality, this has 5, so there's 5 bonding pairs, no lone pairs around the central atom. So the shape it adopts is called trigonal bipyramidal. So we'll get to that, but just to throw it in there, right? But this is fine as a line diagram at this stage, okay? But that's how you represent the shape. Wedge, that means it's going out, coming out, so it's like it's planar, right? If you were to picture, there's 3 fluorines all in a plane, and then there's one sticking up, one sticking out, and one sticking out. Okay, that's PF5, SO2. So S has got 1, 2, 3, 4, 5, 6 electrons in its outer shell, and oxygen also has 6. So how's this going to operate? Now, oxygen is going to be the one that determines, so it'll definitely have, right, so there's 2 oxygens. So each of those, because they're kind of, the central atom tends to be malleable, like changeable in terms of its, how many electrons it'll accept. So what you have here is, you've SOO. Okay, put in our oxygens. Each of those will definitely, there'll be a double bond, because each of the oxygens will have to have 8 electrons, right? We'll have to have all the electrons paired, okay? Now, and then that means we have, oh, I should have changed the colors here, or the format anyway. I should have made those X's. Okay, so we've got 2, right? We're definitely going to have pairs, right? So now how many electrons have we taken care of? We've got 2 left, so that's the 6 in total. So they're going to go there. So you can see here that this sulfur ends up with 6 electrons. No, it ends up with 10. Okay, electrons around it. Okay, so more than 8, but they're all paired. That's the main thing. And here you have a lone pair. And you have 2 bonding pairs. Now they're double bonds, but that's how we're going to classify them. And actually, so to draw this, you could do that, okay? But actually, in this instance, it just happens to be bent because actually that lone pair is going to push those away, right? Okay, so that's actually a bent shape. What have we got next? Carbon dioxide. I'm going to skip carbon dioxide because again, you've seen that. That's the GCSE. I'm going to skip 11, which is ammonium, because we've already done that. AlCl4 minus we are going to do. So number 12. AlCl4 minus. We did see it. But it's actually tetrachloroaluminate, I think it's called, because, well, I know it has no oxygen, but we're not worried about that for now. Okay, so you've got, okay, so aluminium, 1, 2, 3. Okay, so it's got 3 electrons, so it can form 3 covalent bonds, unless it has accepts a pair of electrons to form a coordinate bond. And you've got the chloride ions, or 1 chloro, let's see. 1, 2, 3, 4, 5, 6, 7 by 3, and then you all have, we'll assume that the minus charge is on one of the chlorines. So we have a Cl with 1, 2, 3, 4, 5, 6, 7, and then we're going to just put this, we'll assume it has an electron from a metal. Okay, so it's a chloride ion. Okay, so how are these all going to combine? Right, your Al, let's put its electrons in, and we Cl's, 2, 3, 4. Okay, so, oh, I did it again. I should make those X's. So the board comes in handy. Okay, so we've got just regular covalent bonds. So your 3 chlorine atoms, and then this, you're going to have a dative covalent or coordinate bond. So a coordinate bond between, doesn't matter which, but between the chloride ion and the aluminium. Well, it will be between the chloride ion, and that is. And remember, I'm just going to show, even though an electron is just an electron, I'm going to show that extra electron because the negative, the overall negative charge. Just there, and if you're to draw it, it is and if you're to give it a shape, seeing as we're mentioning it, it's actually tetrahedral. Right, it's a tetrahedron. Okay, 4-sided. If you were to connect them all up and put faces on that shape, you would get a tetrahedron. Okay, next one is BCl3. Okay, so boron, group 3, 3 electrons on the outer shell. Okay, chlorine needs 1, so they're both going to form, there's 3 of them. So you're going to form straightforward 3 covalent bonds. Okay, and that's it, and this will be BCl. Okay, so you can draw it like that. Now in reality, we've got 3 bonding pairs around the central atom, and they will separate as far apart as possible. So actually the shape ends up as trigonal planar, right? SS6. Okay, so sulfur. Actually, easier to draw. And sulfur is group 6, 6 electrons in the outer shell. Fluorine group 7, 7 electrons in the outer shell. You've got 6 of these. And you're going to use all of these electrons, right? So S, 4, 5, 6, and let's put it in. 1, 2, 3, 4, 5, 6. I hate drawing this one, it's fiddly. Okay, and electrons in. Okay, and that's, you could draw it like this as the line diagram. That's pretty close to its actual shape. It's called octahedral, the shape. So it's like okay, so this bonding pairs around the central atom. Next one is BeCl2. Put that down here. So beryllium and 2 chlorines. Beryllium has 2 electrons in its outer shell. Chlorine has 7. Okay, so you're going to form 2 covalent bonds, 2 single covalent bonds between boron and chlorine. Sorry, beryllium and chlorine. And that is represented like this. And actually, it's the same line diagram, but that's actually its shape. It's a linear molecule, right? Next one is, this is a weird one, BeCl4 2 minus, which implies that you have to add a chloride ion to a negative BeCl3 minus, which is already negatively charged. Anyway, if it exists, it exists. Okay, so this time how it's going to work is beryllium. Right, so if we've Cl4 2 minus, that means we've 2 chlorine atoms and 2 chloride ions. Okay, so let's see how that will look. There's 2 of those, and then I'm just going to do the electron from the, so that's chloride ion by 2. Okay, so how's that all going to go together? So there must be, this can only form 2 covalent bonds, and 4 covalent bonds in total. So 2 of them, the extra 2 must be coordinate bonds. So let's have a look. Be. Okay. So there's the ones, the chlorine atoms, regular covalent bonds, if you like. Form atom, each atom puts one electron into the shared pair. And then the chloride, so now you have coordinate bonds. And the outer shell, that electron is paired with an electron from a metal, presumably. And then overall, it shows 2 minus. And how we draw that. So 2 of these are coordinate bonds. It doesn't matter which 2, as long as there's only 2. Okay, and the actual shape, because it has 4, there are 4 bonding pairs around the central atom, it'll actually be tetrahedral. Okay. IF4 minus. Now this is messy. Right. I know it's an interhalogen, well, molecular ion. They do bond with each other. Right. So iodine has 7 electrons. You can just take, even though I know it's got obviously 3 Ds and 4 Ds, and all that, you can just take the outer electrons of 7. So 1, 2, and fluorine also has 7. So how's this going to work? So we have 1 fluorine and 1 fluoride. Okay, which implies one of these is going to be a coordinate bond. Okay, so fluorine that down. And that's by 3. Let's give it a different format. Okay, and that's by 1. It's 1 fluoride. Okay, so we can only have single covalent bonds here. So we've got 4 single covalent bonds. Actually, I don't think there's any coordinate bonds in this one, because if we do coordinate bonds, that ends up with an unpaired electron, does it? Right, let's do the 4 bonds first. Okay, so let's put F. I need to leave room for the unpaired electrons, the lone pair electrons. Okay, so let's do, we've got, no, one of them has to be coordinate. Okay, so let's put these in. So we've got 1, 2, 3, and a coordinate. And then in terms of electrons from iodine, 1, 2, 3, and that will leave 4, so 2 pairs, which gives it an even number, right? And then we've got, let's put in the fluorine atom electrons. And then here's its extra electron. I'm trying to think what shape. That would be a square pyramid shape, but happily not on the specification. Excuse me. Right. Okay, last, right, so that's IF4. Right, C2H2. Okay, so hydrogen can only have 1 covalent bond, and carbon can have 4. So how are we going to make this operate? And just be aware the carbons will always be bonded to each other. You won't have to worry about any other situations for now. Okay, so we're going to have, it's a carbon, 2, and hydrogen. I'm not even going to change it. This should be easy enough. Hydrogen has 2. Okay, so let's put them together. And at least put the hydrogens in. So we've got single covalent bonds between each of the hydrogens. Hydrogens and carbons, and now everything else is going to get shoved in the middle. So you've taken, right, each carbon still has 3 electrons. So in they go. going to look is, oh, this is beautiful, and we don't actually study it, but you know, they do throw it on the all pass paper. This is called ethine. It's a homologous series called the alkynes. So if you remember anything from GCSE, I'm sure you remember it very well. Alkanes have they have just single bonds between the carbons. Alkenes had one carbon-carbon double bond, and alkyne is the next kind of hydrocarbon. But they don't do it GCSE or A level, but they do sometimes ask this type of question. Right, so it's homologous series alkyne. This is called ethine because eth two carbons, YNE is an alkyne. Okay, anyway, that's what it looks like, and it is a linear molecule. There's no lone pairs anywhere to be seen. Okay, next one is SO42 minus. Right, so have a think about this one. Okay, how's this going to operate? We've got a sulfur. You see, sulfur is sulfur can handle more than 8 electrons around the center. We've got 2 minus means, well, it could mean O2 minus, but then it doesn't. Okay, if there's oxygen, then there's a charge. It means you have 2 O minuses effectively, right? I mean, let's see, we've got actually in this instance, I think the best way to work this out. Four of those, and let's put O minuses in because we've got to make it more obvious why there's some single and some double bonds. Okay, so that has a negative charge, right? So it still needs. So this will form two bonds. This needs 2 covalent bonds, and this just needs 1, right? And sulfur will oblige. I'm changing my format here. So 1, 2, 3, 4, 5, 6. Okay, so let's see how many of these electrons is going to have to be in a covalent bond. So we have 2 of these. Right, so you're going to have 2 double covalent bonds. Let's do those first. Okay, so let's put those on. So 1, 2, 3, 4, and then the oxygen. Okay, and then there 2 lone pairs. Okay, so those oxygens are taken care of. They each have a double covalent bond. Now, these guys will have single covalent bonds. So that's all they need. They already have one of their electrons paired up, thanks to an obliging metal, as I assume. Okay, now fill in the rest. And the electron has a minus charge. So it's gained 2 extra electrons in that ion. And we're missing, oh yes, last thing is to account for all, just see if there's any lone pairs left on sulfur. 1, 2, 3, 4, 5, 6. No, there are not. Okay, so how are we going to draw this? This is, okay, or you could put, yeah, I think for this sulfate ion, best to put the minus charges directly on it. Could do this. And bracket the outside. That would also be legit. And in terms of shape, it has effectively got 4 bonding pairs. Right, so it'll will be tetrahedral. We've seen tetrahedral before. Anytime you've got 4 bonding pairs, the equivalent to 4 bonding pairs, you're going to have a tetrahedral molecule. We're nearly there. Nitrate. Oh, we are there. Nitrate is the last one. I've actually done nitrate already, but I'll do it again. So you've got nitrogen and you've got NO3 minus. That means you've, let's see, one of the oxygens has gained an electron already. So you've got 1, 2, two regular oxygens, if you like, and then an oxygen that has already gained an electron, has minus charge. So these need 2 covalent bonds, these need 2 covalent bonds, this needs 1, right? Nitrogen, what can nitrogen give? Nitrogen has 5 electrons in its outer shell, so it can, in theory, do 5 covalent bonds, and if it does, it's going to take care of those 3 oxygens. So let's see how that works. Okay, so nitrogen, all 5 of its electrons are going to be, oops, all 5 of its electrons are going to be involved in bonding. So let me leave room for the oxygens pair. So 2 doubles, 1 single, no coordinate bonds. And then we've got okay. Minus on here, and how would we represent that? Oh, I've just realized. Could do O minus. I think, didn't we see something different? That's certainly valid. I'm trying to see, is there, I think maybe nitro has a coordinate bond. This model certainly works for bonding. See if there's an alternative. No, I think I'll keep that. That makes the most sense. Anything fancier than that, you certainly wouldn't need to be worried about. As long as you can make it all, you can account for all of the electrons, so everything's paired. You can identify what difference the minus charge makes.